Okay, so we have a warm-up. We have the function. It's the integral from x cubed to 4x of 11 over the square root of 2t squared minus 7 dt. And we're asked to find f prime of 2. We have some options, -8, -4, 0, 4, and 8. What's the answer? A is right. -8. All right, so what are we using here? What's the tool? Fundamental theorem of calculus, right. It's a really good answer. So essentially, whenever you see integrals and derivatives involved in the same problem, fundamental theorem is probably lurking somewhere. So you say, all right, well, I want to find f prime of 2. Let's start by finding f prime of x. So what do? You start by saying, all right, you take the top, which is 4x, and you plug it in everywhere where you currently see a t. So that's 11 over square root of 2 times 4x quantity squared minus 7. And then chain rule it. Don't forget times the derivative of 4x. But not to be outdone, you say, aha, don't forget to subtract. What happens when you put x cubed in? And so everywhere you see a t, you put an x cubed. And again, you chain rule that. The derivative of x cubed is 3x squared. Now you put in 2. 2 is chosen so that some parts of it would turn out to be pretty nice. So if you look, 2 gives you 8 for both upper and lower functions. The 8 is 2 cubed, 8 is 4 times 2. 8 squared is 64, times 2 is 128, subtract 7 gives you 121, which we probably recognize that's 11 squared. So you end up with 11 over the square root of 121, which means that both these terms become 1. So you end up with 4 minus 12, -8. Nice, nice. All right, any questions on what we did last time? Okay, well, in that case, our thought for the day, I never look back, darling. It distracts from the now, from the great designer Edna Mode. And, well, perhaps not the intention was to what I'm about to say, but the spirit is the same. This is sort of a Zen approach to life. Don't dwell too much on what happened in the first part of the course. Focus on the now. Focus on getting ready for that exam. That's your priority. Worrying about what came before, you can't change that, but you can change what comes next. So make sure you invest in yourself. Spend time, study, prepare, be ready. You'll do okay. I believe in you. All right. So today is a great subject. Favorite part of integration. So we're going to learn about substitution. So let me just talk a little bit about where it comes from, and then we'll go through the details. When we started talking about antiderivatives, we said there's this underlying mantra. Rules for derivatives become rule for antiderivatives. So, for example, when we saw that the derivative of sine x was cosine of x, we said, aha, flip it. That says that the antiderivative of cosine x is sine of x. That's an example of what we mean by that. We also said, there's some generic rules, like derivatives are linear, antiderivatives are linear. But the most important rule, and when it comes to doing integration, this is probably the most important thing you need to master. We start with the chain rule. So remember the chain rule says if I have a function in a function, and I take the derivative of the outside, leave the inside alone, times by the derivative of the inside. Well, pull out your fundamental theorem of calculus and imagine that you integrate both sides. So the integral of f prime g of x times g prime of x dx, well, what do you get when you integrate a derivative?
Nothing.
Well, you get back to where you started, f of g of x. Now, technically, this is not correct. What would be correct? Plus c. So we want to be technically correct, right? We love technicalities. All right. So what's the idea of substitution? Well, essentially our idea is we're going to put a new variable to help simplify the problem. And this is the art of calling names, name calling, if you will. So if you have any young siblings or perhaps nieces and nephews, you can be like, I've been learning how to call names. You're like, yes, me too. My kindergarten class is vicious when it comes to name calling. All right, so what's our setting? When we have the integral of f of g of x times g prime of x dx, we're going to introduce a new variable. So substitution is often called u-substitution. Doesn't have to be u, but it often is. And we're going to introduce a new variable. We're going to call it u, which is the inside part. So here's u. And then we're going to say, well, du is g prime of x dx, which is this piece on the end. So we have your u, your du. And now we say, instead of working on this integral problem, we can work on that integral problem. And this is, there's a technical term for it, nicer, because there's less stuff. It simplifies the problem. And we like things to be simple. And there's a note here. What are we doing? Well, we're introducing a new variable, but essentially what we're doing is we're just updating it. We're replacing all of the x's. Not just some of them, all of them. Every x is going to get replaced in terms of u. And that especially includes the dx. So don't forget to update this. And so that's one of the reasons why we keep emphasizing you need to write the dx. That's important notation because it is part of integration. Now, we're going to do basically almost all practice today. So this is most of the theory. So I want to get it all out now. How do you find the substitution? I say it's the most important rule. It's the one you'll use most often beyond just knowing your basic integrals. How do you find it? Well, you need to know what to look for. And to understand that, you think about where does it come from? So we say, well, we know where substitution comes from. It came from the chain rule. Chain rule had a function in a function. And so we're like, so what should I look for? I should look for the function that's on the inside. So I sometimes tell my students that the u-substitution it's an inside job. What's the function on the inside? So that's one place to look. Now, it's not the only place to look. There is a second place to look if it's not clear. What's the function on the inside? The other place to look is saying, well, you have to have this g prime of x. So we can start saying, well, is there anything that's a good candidate for g prime of x? Because if we know g prime of x, we could find g of x. Well, what are we looking for? We're looking for some piece of it which is easy to integrate, just that piece. That could then be a potential substitution to make. So those are our two things. Find a function on the inside, look for some piece of it that's easy to integrate. And those are your two places to look. Now, there are some challenges that come into play. There might not be what we need in the g prime of x term. That's okay. We have ways to deal with that. We'll do at least one example. The punchline is, we know what u is in terms of g of x, so we can use that to say, instead of saying g prime of x dx is du, we can say, dx is stuff with u du. And I should add a little note here. Note. Constants are easy to move around. I knew I would forget something. Okay. We'll see what that means as we go on. It's okay to do multiple layers of substitution, which says, okay, I tried a substitution. It did make it a little bit simpler. And then I said, oh, there's another substitution I should make there. No problem. You just say, all right, my first layer, I'll introduce u. And then you say, well, I want another layer. What can you do? You can do w. And I say, well, I want another layer. What do you do? Triple u. You can have as many u's as you like. Or you could maybe use different symbols, but okay. But the point is, you can have multiple layers. I think I skipped I thought it looks like a pentuple u. But anyways, important thing, eventually our goal is simplify, simplify, simplify until we can integrate. Once we integrate, we have to go back. We have to get back to where we started. If our integral problem started with the variable x, our answer has to have the variable x. Anything that we introduced to help has to be taken away. So make sure whatever variable was there at the start, that's the only variable that shows up in your answer. All right. That's the overall idea. I think practice will help a lot. Any questions? Okay. I do want to mention there is sort of an overall plan for antiderivatives that almost every single time you're faced with an antiderivative problem, in the back of your head you say, there are like 8 antiderivatives I know. These 8. And if it's not one of these 8, you're not going to take the antiderivative of it. So you're like, well, what can I do? Well, first off, is it one of your basic ones, one of these 8? You're like, yes, you're happy. No? Can you do some algebra or trig to rewrite it? Yes? Okay, then check to see if it's something that you can do. No? Is there a good substitution? If there is, do the substitution. Now is it one of the ones you can do? Otherwise, keep going. And ultimately, if you get stuck, there's a nice option. Next semester, take Calc 2. Will we introduce a lot new variables? No. Will we introduce a lot new antiderivatives? No. Will we introduce new tools? Well, we'll introduce one new tool, but we are going to be like pulling out the sledgehammer in algebra and trig. A lot of calculus is algebra and trig. The name of the game is rewrite it until it's something you can actually do. The calculus part is very short. So, fun stuff to look forward to. All right, let's begin. And some of you may have had calculus before, so this will feel very familiar. And if you haven't, don't worry. We'll get to enjoy the journey together. All right, so we have some problems here. Find the following. There's 3 of them. We're not doing them all at the same time. Which one do you want to start with? Start with the first one. Sounds like a good plan. We have the integral of 2x e to the x squared dx. That's not one of our basic 8 integrals that we know. There's no algebra we can really pull here. So we start thinking, is there a substitution? So, is there a good candidate for us? And if there is, what is it?
E to the x is in the middle, right?
Well, think about, you have to be careful with notation. So when we write e to the x squared, it means the x squared is the inside of the exponential. So it's not, so e to the x squared is not the same thing as e to the x squared. So we are in the first case, where x squared is inside the exponential function. Ooh, is that a clue? Did he just say inside? Or maybe it wasn't a clue, I don't know. It's only a clue if people pick up on it. 2x is the derivative of x squared, that's true. So what are you suggesting as our substitution? The x squared. It's like, hey, I see a function in a function. So we'll try that substitution. U is what we're calling x squared. So then du is 2x dx. And we're like, it's almost as if they had planned it. Because we did, because these are our warm-ups. So the punchline is that if we can integrate the following, where we replace x squared by u, and replace 2x dx by du, figuring out how to do this integral is the same as figuring out how to do that integral. But this one is simpler, and we like simple. Is this one that we can do? What is this integral? E to the u. Toss on a plus c so we get our points. Is that our answer? No, because what's missing? We need to get back to x's. We started with x's, we need to end with x's. So how do we get back to x's? Yeah, we know what u is, so we get e to the x squared. Now, I don't know if we've said this, but let's say it right now. Pro tip, how can you check your answer? How do you check antiderivatives? Yeah, you check antiderivatives by taking a derivative. So when in doubt, you take a derivative and see if you get the right thing. So it might help to convince you that this is doing what we claim. What's the derivative of e to the x squared? It'd be chain rule. Derivative of the outside is just the exponential function. Leave the inside alone, so that's e to the x squared times the derivative of the inside, which is 2x. So this is, in fact, the right antiderivative. So what's going on is that you really are doing the same problem. It's just that these extra pieces, which are sort of obfuscating what's going on, gets embedded inside of your new variable. All right. Second integral. Sine e to the theta times e to the theta d theta. What's our substitution? E to the theta. Why e to the theta? It's on the inside. That's a good reason. So what is du?
E to the theta d theta.
E to the theta d theta. Ah! Nice! So what does this integral become? Sine of u du. Is that one of our basic integrals that we know how to do? Yes. What's the integral of sine? Negative cosine or positive cosine? Negative. Good, 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 good. Okay, is this our answer? Got to go back, right? We got to get back to theta. So negative cosine e to the theta plus c. All right. Our last one. Integral of 3t squared plus 1 times the t cubed plus t to the fourth. Now, there are ways that we can do this which don't involve substitution. We could take t cubed plus t and raise it to the fourth power if we wanted to. So, for instance, we all know that t cubed plus t to the fourth is t to the 12th plus 4t to the 9th plus 6t to the 6th plus 4t cubed. Whoops, I forgot about that t. Oh, it's even worse. Okay, it is t to the 12th. plus 4t to the 10th plus 6t to the 8th plus 4t to the 6th plus t to the 4th. Then we could multiply by 3t squared plus 1, so we get a polynomial, and then we can integrate that polynomial. And that's great. We'd get the right answer, but odds are pretty good we'd probably make an algebra mistake before we got to the end. Our goal is to try to get to our answer quickly, as simply as possible. The more simple we make the process, the less likely we make mistakes. And then we get points. Oh, we love our points. We want all of them. Okay, so let's see if we can do it without having to do the algebra. Do we have a candidate? T cubed plus t. That looks like a great candidate. All right, so let's see what happens. If you let u equal t cubed plus t, what would du be? 3t squared plus 1 dt. And almost like it was planned, because it was. We do have a 3t squared plus 1, so this is a great substitution. Not every substitution works, but we try something. If it doesn't work, try something else. And if it's like a USB, if it doesn't work, we try it one more time, but push really hard, right? That's how we make things work. Okay, so what is our new integral here? U to the 4th du. Do we know how to integrate u to the 4th du? What is it? 1/5 u to the 5th plus c, and then put back what u is. So 1/5 t cubed plus t to the 5th plus c. And that seems a lot easier than what this was turning out to be. So look for ways. We have ways. Yes? All right. Now that we've got the warm-ups, are we ready to go and do some that are slightly more challenging? Okay. Now this has a note. You might need to rewrite before doing a substitution. Okay, so let's look at this. Let's just say, I have an idea. I see this z to the 6th plus z is inside something to the 4th power. So let's try it. U equals z to the 6th plus z. Great. What would du equal? 6z to the 5th plus 1. And then when we see this, what do we say? We're sad because there is no 6z to the 5th plus 1 available to us. Oh, it's like that Mario theme music when he didn't make it. Dun, 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 dun. Okay, so that's not a good substitution because we can't account for the du. So what do we do? Give up? No, that's not like us at all. We would never. Can we do anything? Well, remember, we are allowed to rewrite. This is also known as algebra. So, is there anything we can do algebra-wise? We can, notice the inside has a z. They both have z in common. So this is like z times, z to the 5th plus 1 to the 4th. So that's like z to the 4th times z to the 5th plus 1 to the 4th. So that's our algebra. We're rewriting. Now, what can we do? Let's try something here. What's a candidate? Z to the 5th plus 1. Okay, well, let's see what happens if we try that. We try u equals z to the 5th plus 1. What is du? Five z to the 4th dz. And we say, well, good news, we got a z to the 4th, we got a dz, but we don't have that 5. But what do we know about 5? It's a constant. It's a 5. And constants are easy to move around. Now, there's a couple of schools of thought. Here's my school of thought. I'm going to use my advanced marker technology and divide both sides by 5. So that I can say 1/5 du is z to the 4th dz. That's one way to approach it. Another way that people like to approach it is they say, well, let me put a 5 in here. I'll put a 5 right there. Well, how can I put a 5 right there? Well, the answer is you write it. But you say, that's cheating, Steve. You can't just write a 5. Well, that's true. I can't just write one 5, but what can I do? I could write 2 5s. But not just any 2 5s, right? I'll put one upstairs, one downstairs, and what's the net effect? 1. Multiplying by 1 is okay. So that's the other school of thought. Now, like I said, pick one, don't pick both. So I picked this school of thought. All right. With this change, you both end up at the same place, regardless of which way you think about it. What does the integral become?
U to the 4th du.
There's a u to the 4th du, and there's one other thing. There's a 1/5. All right, do we know the integral of u to the 4th du? One-fifth u to the 5th. Well, a 5th times a 5th makes a 25th. And then we say, well, what's u? Z to the 5th plus 1. And then we're done. All right. Cool. Good times. Good times. All right. Any questions on that one? In that case, here's another one. And this one showed up on an exam. So they love this one. They really love it because it also showed up in old lecture notes. So this one is loved by all. All right. Find the integral of dt over e to the t plus e to the negative t. And I know what you're all thinking. Isn't that just hyperbolic secant, Steve? Yes, I know that's what we're all thinking. But let's pretend like we don't know that. All right. So with that out of the way, what can we do? What can we do? Sorry, what? Pull the dt out? Well, we can't pull the dt out of the integral. We can always push it to the back of the integral. That's perfectly fine. Now, what do you notice about this? We have two exponential functions, but they're kind of not simpatico. One of them has t. One of them has minus t. That's not cool, man. Not cool. We'd like them to be kind of more similar to each other. Is there any way we can rewrite so that they both look like, let's say they both look like e to the t?
You could change e to the negative t to e to the t on top.
Could we? How do we do that?
You could split it into 2 fractions, right?
Can we? Oh, be careful. You have somebody who loves algebra here. We remember this plus sign downstairs? This is your dangerous plus sign. That's the plus sign that you have to work for. Plus signs upstairs, split away. Plus signs downstairs, take Calc 2. But I feel like I just gave away the answer now. We already know where this is going to end up. It's clear where this is going. Ooh, interesting. Factor an e to the negative t out. Yes, we can. So I'm going to do it as you've suggested. No, we're going to end up at the same place. Can I do it in a slightly different way? It's going to be equivalent to what you said. If you saw an e to the negative t out in the wild, what does the negative tell you? It's like a fraction. It's downstairs, right? So, like everyone's like, oh, of course. That's another way to write it. But I don't like fractions inside of fractions. Fractions in general, I've had a hard time with them. I've lost a lot of points due to fractions. So how do we get rid of fractions in fractions? Yeah, we can do a common denominator and flip things. Yep. I guess you could say that there's a infraction going on here. So one of the things we can do here is we can get a common denominator. It's equivalent to doing the following. I'm going to think of this as multiplying top and bottom by something to clear off my fractions. So e to the t. Now this doesn't feel like me factoring out e to the negative t, but that's really what's happened here. Is that the e to the negative t that you've pulled out would end up upstairs as e to the positive t. Okay, so if we do all of that, what do we have? We have e to the t upstairs. I'll put it right next to that dt. Downstairs, what do we have? E to the t squared. Now I don't want to write e to the 2t because I came from a problem where it's like, oh, I have t and negative t. I don't want to go back to my problem like, oh, I've got t and I've got 2t. I want all my e to the t's to look like just e to the t's. Okay. So, does that look like anything? Is there a substitution we can make now? E to the t? Yes, I agree. Good. It's on the inside of something. Let's try it out. Try something. If it doesn't work, that's okay. We've learned not to do that. And if it does work, points. What's du? E to the t dt. So when we talk about d, it means take a derivative. So it's like, here's our du. So what does our integral become? du over u squared plus 1. Now that looks a little bit simpler. There's no exponentials involved. Now, is that on our list of things we know how to integrate? You betcha. Oh, yeah, you sure, you betcha. What is it? Arctangent. And now it's like, oh, I could see why Steve was so excited this whole time. I should have known. As soon as he was happy, I should have known there was an arctangent. All right. No, I'm always happy. I'm a happy guy. Okay, are we done?
Nope.
What's left? Yes. So this becomes arctangent of e to the t plus c. There we go. All right. Any questions? Are we ready for the next one? Nice. Okay. Find the integral of y cubed square root 9 minus y squared. Or as they say, what do we do? What do we do? Now, can we say, oh, square root of 9 minus square root is 3 minus y? No. No. That would make it easy and I'd be out of a job. So we don't allow that. No. Square roots does not work well with addition and subtraction. That's unfortunate. So let's try something. What can we try?
Make it into a 1/2.
Okay, so we'll get there. Sure, we can start that. Integral y cubed. 9 minus y squared to the 1/2. Okay, what else can we do? Thinking substitution. Let's channel our inner substitutor. Why do you want u to be 9 minus y squared? It's on the inside of something, right? We're looking for inside stuff. Inside addition. All right, so u equals 9 minus y squared. What would du be? Sorry, what? Somewhere. Almost 2i. Negative 2i. Very good. And dy. Okay, now there's not a 2, no problem. We can write this as minus 1/2 du is y dy. Okay, so are we good to go? Do we have a y dy? We have a y cubed. Oh dear. Oh dear. Let's pull some stuff around. We can rewrite it. We have a y cubed. Let's pull off a y. So we have y squared, 9 minus y squared to the 1/2, y dy. So the y dy we're happy with. The 9 minus y squared we're happy with. Can we do anything about this y squared? Or is this just not going to work as a substitution?
Could you make it a negative and put it in the bottom since it's being multiplied to that?
But what a negative?
Like the exponent y to the negative 2 and put it on bottom?
I don't think it would help us. We could try it, but there's something a little bit more direct. What's the mantra you have? When you're making a substitution, you need to replace which of the y's have to be replaced? All of them. That's the key. Now, and you might say, but this is just doing some of them. And like, that's okay. You still have a relationship. U equals 9 minus y squared can tell you how to get some of the stragglers. What's another way to write u equals 9 minus y squared? Y squared is equal to 9 minus u. So now we're like, y squared, I like that. Because I can write that in terms of u. My goal is to write everything in terms of u. And it might take a little bit of rewriting. That's what we're learning here. But we can do it. We have the technology. So, what do we have? Y squared, 9 minus u. 9 minus y squared to the 1/2 becomes u to the 1/2. Y dy becomes minus 1/2, which I'll pull out, du. Okay, does that look easier to integrate? It looks easier. Is it on our list? Not quite. But we don't want to give up hope because we have made progress. What can we do here? We can distribute. The power of algebra compels you. So, what do we have? 9u to the 1/2. U times u to the 1/2. U to the 3/2. Can we do that? Yes. Whew. We got to the point where it's like, we can do this. These are pieces on our list. Happy days. Okay, so what's the integral of u to the 1/2? U to what power? 3/2, we add 1. Anything else? There's a suspicious gap here. Sorry, what? Multiplied by the reciprocal, 2/3. Very good. Okay, what's this one going to be? Good. Someone said 2/5 u to the 5/2. And then don't forget a plus c near the end. Don't forget about this -1/2 multiplying through. So I'm going to use that to change the order, just because I like to have positive terms in front. 1/2 times 2/5 will give us 1/5. The 2's cancel. So 1/5 u to the 5/2. Here, 1/2 and the 2/3. The 2's will cancel. The 3 goes into 9. So what we'll have left is minus 3u to the 3/2. And plus c. Is that our answer? No. What do we need to do? Yeah, put back u is 9 minus y squared. So 1/5, 9 minus y squared to the 5/2 minus 3, 9 minus y squared to the 3/2 plus c. And there we go. Woohoo! Nice! All right, I think we can do one more. Oh, there's so many good ones to choose from. So many. So many. Don't worry. We also have next time. All right. You ready for the next one? Any questions? Yes? Did I make a mistake? Don't worry. I won't feel bad if you tell me I made a mistake.
On the, like with the cancellations.
Right? Which? Uh-huh.
Is it not 6? 3, 2,
Is it not 6? Well, because we had the 2 and the 2, right?
Oh, okay.
So it becomes 2/6. That's plus to 1/3. Right? Yeah. Yeah.
Wait, what?
No, you just, what I'm saying is that you basically take 1/2 times 2/3, and it becomes 2/6, which simplifies to 1/3.
I believe you.
Okay.
Okay, good. We all believe each other. Nice. Nice. Full points for everybody. Okay, a nice cool down problem. All right. The integral of 1 over the square root of 1 plus the square root of x. Okay. Cool down, relaxing. Any place we can start? Math Resource Center. Okay. Unfortunately, I don't think we have time to get there before class ends. Now, we might be lucky. This might be one of our 8 integrals we know how to do. We're not lucky. It's not on our list. So what can we do? There's not a lot of algebra available to us. So let's channel our substitution. Does anything look like a good candidate for substitution? Sure. This 1 plus square root of x, it's all on the inside. Let's choose that as our substitution. Let's see what happens. So we're going to let u equal 1 plus square root of x. And I know that I've made that much harder to see. There we go. Nice. Now it's easier to see. All right. So there's our u. What is our du? And this is the same as 1 plus x to 1/2. So du, we're not integrating, we're differentiating. Yeah, so the 1 goes away, 1/2 x to the minus 1/2 dx. Now, this, by the way, is the same as 1 over 2 square root of x dx. Okay, so cool. There's a problem I see here. I don't have that. There's no something over square root of x in this expression. So does that mean we give up? No. No. We're not giving up. We want all our points. We deserve our points. We're going for it. You might think that like Steve just cares about points, but I like getting the stickers that say good job. I want that. Okay, so here's where we get to do this is a deeper dive into substitution, right? We're going to do some weird stuff. So this is the same as saying dx equals 2 square root of x du. We're going to try really hard with this substitution because like we don't have any other clue. So we're like really going for it. Now, this is good in some sense, but it's not great in another sense in that we still have x's. We want to get all the x's gone. I don't want that square root of x left after I carry out my substitution.
Make it 2 parentheses u minus 1.
Oh, someone has cleverly noticed. Almost as if it was planned. Because it was. I didn't plant you in the audience, by the way. I just want to be clear. Square root of x is u minus 1. So this is 2 times u minus 1 du. And that is good. I'm replacing everything with x in terms of only things with u. So, with that in mind, let's see what this integral becomes. And what do we have? We have the integral 1 over square root of 1 plus square root of x. I'll go ahead and write that as u to the minus 1/2. That's this piece. Then the dx is 2 times u minus 1. Now, does that look more palatable? Like something you might be willing to at least introduce to your friends, if not your immediate family. It's not quite so bad. What can you do? Distribute. So this is, pull the 2 out in front, u to the minus 1/2 times u, also known as u to the 1/2, u to the minus 1/2 times minus 1, minus u to the minus 1/2. And now we're like, nice, because these are on our list. All right, so finishing up, because we're basically out of time, add 1 to the exponents, so 3/2, multiply by the reciprocals. Do the same thing with the other one. Add 1, u to the 1/2, multiplied by the reciprocal, 2 over 1. Add c, so 4/3, u to the 3/2, minus 4, u to the 1/2, plus c. The last step, replace u by 1 plus square root of x. So 1 plus square root of x to the 3/2 times 4/3, minus 4, 1 plus square root of x to the 1/2 plus c. And there we go. And if you're like, oh, I really could use a lot more practice with substitution, I have great news. That's all of next lecture 2. So we're going to get really good at this. Have a good day.